Okay, so good evening to all of you. Today we are going to see how to make use of multisim to perform some experiments on non-inverting amplifier. So let's go and see how we can use multisim for the first time, and then beginners can start seeing some YouTube videos to get more insight into it. So I have right now installed multisim. So if you can see, this is our multisim window. When you will open multisim, you will find this kind of windows. So this is called workspace or workbench, where we are going to place our components. So here we can complete our experiments. For fast forward, I will show you how we can place components. So I can directly go and I can check our op amp. I can take op amp from this packages which is available here. So 741, I can just select. So this is the place component, and component can also be chosen from here. You can, if you press component, then you will see a list of components here. If you see select all group, here also you can put some component. Let's suppose I want to choose 5 volt source. So source I will put. So it is not coming. Let's suppose resistance. So you can get resistance here. So in resistance also you can find resistance in basic also. If you go to basic, you can find resistance. You can select your sources. Some few sources are here. You can see power sources are there, signal sources, signal voltages. So let's suppose to you have already seen in inverting non in sorry inverting amplifier, you have already seen you are required to give biasing on pin number 7 and 4. So let's suppose I am choosing VE and VCC. So here I have chosen VE, and this is to be rotated, right? Because I have to connect it to pin number 4. So I can rotate by using Control R, or we can select, and then we can select by dragging mouse, and then we can put right click, and then we can rotate. Okay, so rotate is you can see clockwise rotation is Control R, and anti counterclockwise rotation or anti-clockwise rotation is Control Shift plus R. So I have just now told you Control R will be good enough to do all the rotation. So now if you connect it, what you have to do is just you have to bring your wire, bring your mouse to the point where you want to connect. So here let's suppose I want to connect these two. I will drag, and when I will get a red drop, I will leave. So now you can see it is connected. If it is properly connected, it will become red. We can also change the color in case of output. We are going to see, if you want to see input and output of two different color, then here we can change our net color also, and it will change the corresponding color if we do apply. So you can see I have changed the color from red to some different customized color. So this is the way we have to take the components from the drop down menu or from place. So this is if you can see, this is I have downloaded, and I am using right now the evaluation version of it. So you can also download and make use of evaluation version for learning purpose. However, my intention is not to promote multisim here, but we can use multisim as one of the tool to simulate our experiments for both for EDC as well as for linear electronic circuits, and we can also perform a lot of digital simulations using multisim. However, you can also download and see some open source like circuit maker, and few open sources are also available which can be used for simulation, and it will be very much enough for our lab to conduct our whole experiments. So this multisim will give you simulation based result. Now let's quickly go into our main simulation, which I have already prepared and saved it as non-inverting. So now intention of this experiment is to see our op amp as an non-inverting amplifier, right? I have just now told op amp as an inverting amplifier. We have already seen through simulation, so already seen through our components. We have placed the components, and now as all students are virtually at very far place, so if you are not finding components, you can directly make use of this, and you can observe result. So now if you can see, I have a facility of function generator. So from here I can see multimeter, function generator, watt meter. So these are the things I can directly download, directly select and put it into the workspace. Once I put all these things, the non-inverting amplifier connection. So this is RF, R3 is RF, R1 is input resistance. So the overall gain of this amplifier will be 1 plus R3 by R1 in this case. So if you donate R3 as RF, then 1 plus RF by R1, and you will see that output and inputs are, um, it is in phase. So let's simulate this. We will run it and we will see what is happening. Now you can see input and output are 1 plus RF by R1 is 2 times gain, right? Because both are same, 1k 1k. So 1 plus RF by R1 is 2 times 1 plus 1 by 1k. So both k 1k and 1k will get cancelled. So 1k and 1k is getting cancelled, means 1 plus RF by R1. So RF by R1 become 1. So 1 plus 1 gain should be 2. So what I have done is, in this oscilloscope I kept both the division 2 volt per division, and I can see output is of blue color, right? Output is of blue color and it is given to channel A. So output is of blue color and it is given to channel A, and you can see that I am getting, I have pressed this reverse. Earlier it will be black, so I have pressed reverse to see it in black and white format. And now I can clearly see both RF and R1 don't have any phase shift, right? They don't have any phase shift, and output is just twice of input, right? So see, if I put my marker here, see, this marker is going on channel 1. All this marker is going to the channel 1, and this is for channel 2, right? This marker, both markers are going for channel 1 and channel 2. So this is red marker, it will give you red values. This will this is blue marker, it will give blue value at this point. So now if you can see, outputs and inputs are, if you can see gain, so channel 1 minus channel 2 is, you make it to exposition 0 volt, this. So you can see gain is approximately 2 times, but you are also expected to measure the frequency response, which can be measured through Bode plot. So Bode plot have 2 types of plot: phase plot and magnitude plot, which you will read in control system. However, for our experiment, just what you have to do is, here in and outs are written, right? It is a Bode plotter which can be downloaded, taken from here. You are just, I have to stop my simulation, and then I have to see, this is body plotter. So just I have to click and drop here. So once you put this, you can see in and out. If you provide what kind of input you are giving to it and what kind of output you are giving, as our input signal is sine wave, I have chosen sine wave of 50 frequency with amplitude 1 volt, peak volt, means peak to peak is 2 volt. So in that fashion it will tell you what output is. So now it will automatically vary the frequencies on x-axis, and it will see the output of gain in y-axis. You can see I have chosen both horizontal and vertical as log scale. So this both are log scale, and you can see now initial value of 1 hertz I am choosing. I can also keep some 0 hertz. Okay, so at 500 millihertz it is not giving anything. At means I will see what is the value. Now you see at 1 hertz it is giving 6 dB, right? So at 1 hertz of frequency it is giving 6 dB. 6 dB is what? 20 log of 2, because gain is 2. So log of 2 is coming 6 dB. And how to find out the 3 dB less? So 6.02 dB is the maximum gain, and then I will go to 6.02 minus 3 is 3.02. I will see where 3.02 is coming. So approximately 3.02. So approximately I can keep it here, and you can see this is my bandwidth when gain is 2. Now I will see what is happening if I change the resistance to 10k value. I will go and I will place it 10k. So now gain should be what? The value should be 10k, right? 10k. Okay. So now value has changed to 10k. I will see what is happening to my output. So initial value is in vertical 0 dB and final is 10 dB. But now here initial value is 500 millihertz. So let's suppose we have to make it 1 hertz, and final frequency should be. So now gain has increased because 20 log of 11. So gain is more than 10 dB, right? So I have to make, let's suppose 20 dB, 50 dB I am making, and I am seeing what is my gain at 1 hertz. So you can see 20 dB, approximately 20.8 dB, because log 10 is 1. So it will be approximately 20 dB, 20.8, because I am getting 1 plus RF by R1. So gain will be 11. Now, if you can see, I have make initial 0 dB and final 50 dB, means in 50 dB scale I am seeing it. I can also make customized. Let's suppose I keep 25 dB. So in 25 dB range, you can get a clear picture. So 20.8 is maximum, then 20.8 minus 3. So 17.6 or something, right? So you can see now 17.8. So you can see now the bandwidth has reduced. So when gain is increasing, my bandwidth is reducing, because the gain bandwidth product will be always constant value, right? So you can now fully understand what is happening to your gain and bandwidth. So I am only using the magnitude plot of this, and I can see, and this facilities can also be extended and make use, we can make use of analysis. And here you can see AC analysis, and then DC sweep. We will change the value of all the value of sweeping, we will see in the entire range. So all students are expected to explore what is DC AC analysis, what is DC sweep. For multisim, you are expected to observe all those things. So I think now you are in better position to understand how can we make use of multisim to understand what is happening. So what I have done is, I have just connected, at pin number 2, R1 is connected and RF is connected between 2 and 6. So I have given a negative feedback, and then I am giving my input signal to the pin number 3. So earlier in non-inverting amplifier we have grounded it, and this input was given to pin number 2. So you can even check and you can see what is happening. And now what you have done is, you have just connected a Bode plotter to see what is happening to this plot. In reading time, what we have done, we were continuously varying the frequency using this. Let's suppose 50 hertz, what is happening at 51 hertz. So now if you get, let's suppose you got a idea that at 89.6 kilohertz, what is happening to my input and output. So at 89.06 kilohertz, you have got that you will have a cutoff, and gain will be reduced, right? It will not be 20.8 dB, it will be reduced. So now let's suppose I keep here 89.6, 89.06, and here kilohertz, and I will see what is happening to my input and output. So you can see output is also distorted. It is not same as the output which was earlier, right? Now it has taken a form of somewhat triangular wave. Why it is happening? It will be a genuine doubt why this kind of things is happening. So you might have read um, slew rate for op amp. So you are expected to measure slew rate. Now slew rate, if I define, it is rate of change of output. So rate of change of output is not infinity, right? If it is infinity, slew rate for ideal op amps will be infinity, but slew rate for practical op amp will not be infinity. If it is infinity, then only it can, in zero time, it can change its output as my sine wave is changing. So sine wave now at higher frequency is varying at very high frequency. And if you can see now, the gain has reduced, right? Earlier when frequency was less, at the time gain was very much high, and right now the gain has reduced. So you can see this couplings and all those functions which were explained in normal op amp, normal experiments, you can even find it here. So I think now I made my point clear, and now rest of the things is to be explored by you. Thank you.